Okay, so we start from what we were doing in the last class. Right. So we had started introducing various variants of attention, right? See, parameters are very central to machine learning and deep learning. Okay. Now, what was happening in this case? So in this case, we said we are not kind of keeping parameters dedicated for this purpose. Okay. Now, now, what does this allow you to do? What does this kind of attention allow you to do? See, ST is same, so transpose of S, that part is same. Now, H becomes WH. So, what is it? What are the dimensions of W? 100 cross 100, H cross H. For us, H was 100. So, this becomes H cross H. Now, will you get the same H? No, right? In which case you will get the same H? When W is identity. So, when W is identity, you get back to this, right? So, if the system so thinks that H should remain H only, it has a way of doing it by learning W as identity matrix and don't do anything fancy. Okay. Now, so at least in theory, in principle, this should be able to learn identity matrix, right? In practice, whether this happens or not, that's a different thing. We don't talk about that right now. So you don't take these attentions, rather you want to make them better. So, okay. Now, there are other variants too. So this was one that I had written. So this is what they are. So this is our basic dot product. So, and this they are calling multiplicative attention. So I am not writing their names. Now let's say EI is written as, so let me just formally write things. So EI is written as S transpose E. Transpose U transpose V H. Now this is the problem with my notations, because they don't match with any other notation. So for us, what will this guy be? What was EI, guys? I kya tha? What was I? So at ith timestamp, right? So at ith timestamp we are talking about, so this guy would be SIT and this guy will be I we were using for TX, right? So HI should come here then. Anyway, let us leave this notation. Do you understand this? What is happening here? So this is yet another matrix like W, but it's a multiplication of two different matrices. Now you do a little bit of linear algebra. How can I write this again? So this is nothing but U S transpose and V H. Okay. Sorry, U is a parameter matrix, V is a parameter matrix. Which one? No. See, there are only finite number of letters in English language. Okay, and we use W. So, because W is used as a weight matrix, so if you don't want to use W now, you want to use some other letter, you will go to UVW. So, UVW. Okay. Now, I need to fix this. So, what was this? I need to fix this for notation. So, EIS transpose H. What was this, guys? How we were writing this? So, we were writing this as ET, okay, and ET, that means ST and right. So, this is what we are essentially doing. If I write H as a matrix, where so H I am writing as H cross Tx. What is Tx? So, total words in my encoder, okay, in that particular sentence, that encoder. Now, 1 cross H, this becomes 1 cross H because transpose, otherwise this was H cross 1. Now, why H cross Tx? Because I have Tx vectors of size H, okay. So, this makes sense. This multiplication will give me a vector of size 1 cross Tx. So, see, I don't want to put subscripts here right now, okay. What I am saying, H is something like this. So, guys, how will this H look like? Help me get that. So, see, H is something like, so ST will get multiplied with H1, okay. So, this guy is my H1. And then I have H2 all the way until HTX. So, this gives me a, so this is H cross Tx. Make sense? And now you basically multiply these two, what you will get is your vector, and that is what we were looking for. So, rather than writing it is a sum of equations and so on, you just write it as a matrix multiplication. This makes sense? Now, you can do the same thing here. This is 1 cross H, this is H cross H, this is H cross 1. So, this multiplication will give you, no, this will give you H cross 1 and 1 cross H cross H, that gives you scalar, okay. So, and if this is not H cross 1, if this is H cross Tx, I'm liking this one more, right? Rather than, you know, talking about Tx, Tx, Tx somewhere in the indices, what we are saying is we are representing this matrix H as where all HTs are columns. Okay, so something like this. Now this whole thing gives you H cross Tx, this gives you 1 cross Tx, that is what we get. Done? It? See, this is just doing what we were doing before. We have just vectorized it. E is your 1 cross Tx. नाम क्या था उसका? What was that name for it? Attention scores. Okay? And then you take softmax of this to get attention distribution. Once you get distribution, what do? So you take weighted average of this H again. In fact, I like this much more because see, now you can simply multiply this with this. Can you? Right? So this was H cross Tx. So this was H cross Tx. If I do something like Tx cross 1 here, I get H cross 1, and that is basically my linear combination of everything. Make sense? So this is which vector? E vector, right? So this is my E vector here, where E is a vector in R Tx cross 1. I want Tx cross 1 because I want this multiplication to make sense. Is it? Okay, fine. Done? So, this makes sense? This makes sense. Why have we added parameters? Short answer is we always do that, and so at least in theory you can say if W is identity matrix, we fall back to this. So if there is, you know, something very special about st.h, then the network should be able to learn W as just identity matrix and do whatever you want it to do as earlier. So this was one type of it. This was the second type of it. I am not really writing their names as they write in CS224N. This is third one. Now what is special with this guy? What is special with this guy? Give me the dimensions of all the vectors. See, this I don't really need to talk about. What is this? H cross Tx. Okay. H cross Tx. This becomes whatever, but this is H cross 1 because transpose is outside. Now what should this guy be? This guy should have second thing as H. Okay. So second thing as H, and the first dimension you can, no, but V will fix it. Okay. So what is V? For V we need to have H here. So wait, this is also fixing it. So the number of what and what? So if this is P cross Q, then this guy must be Q cross R.
So sir, 1 cross H or
Okay.
H cross 1.
So U is Q cross P. So U is Q cross P. So maybe let's say Q is here, Q is here. Does it make sense? So this guy goes and gives me Q cross 1, and this guy goes and gives me Q cross Tx, then transpose 1 cross Q. So this whole thing makes sense, right? Okay. Okay. Now see, people came up with this awesome way of doing. Okay. Then, and this was all coming from hit and trial. Okay. So you can't really prove one is better than the other or another is inferior to another and so on. So there are no mathematical proofs as such. All is your gut feeling, and so you have to work hard to be able to prove that. So you have to empirically prove it that what you were saying makes actually sense. Okay, so then that one, then this one, this is something very important to us. See, now we are diving into the core of this course, which is we are going towards transformers now, and all the terminologies of transformers and LLMs specific to them will start coming now. So we have this. What is happening in this case, by the way? Let us stop here for some time. So this S vector, here what we were doing, so let us compare these two. Here we said just multiply H with a parameter matrix. Here what we are saying, what is so special with just H, you can multiply even S with a parameter matrix. So both of these are, so both, I mean write it down, these are parameter matrices. Okay, so these are parameters. Basically doing the same thing but writing W as two matrices, okay, and then so basically this kind of thing only, but you do more linear algebra on it, learn these two parameters separately. Okay, chalo. So and then they have one more kind of attention, and you can keep on doing this, but this one is really famous. So let me just write it. They say, so EI is equal to V transpose 10H WIH, sorry, W1H plus W2S. Okay, and you can keep on doing this. There are so many variants of it. So, and let me write just 4. What is most important for us is, first we have understood well, second we can relate, third is the one that is most important to us from what we'll do now. So, right. Now, what were the 3 problems that RNNs were suffering from mainly? First was vanishing and exploding gradient. Second was? Right. So that one vector was given the responsibility of representing the whole sentence or whole decoder's output, sorry, encoder's output. What next? Inherently sequential. So we had addressed, so we say that attention actually better caters to everyone, so it in a way solves vanishing gradients problem. What was the second one? Attention goes and attends to everyone, so it takes basically input from everyone, so that bottleneck problem is also gone. Now inherently sequential. So what do we want to do here? See, let me first talk about, so if you go and search the illustrated transformer or JLMR, okay, you'll come across this blog post. This is probably the most famous blog post on transformers. He wrote it. So this is what here. The animal didn't cross the street because it was too tired. Okay. Now tell me, if you were learning this through Word2Vec, what will be the word embeddings of it? Whatever it were, but it will always be fixed. How do you solve this fixed problem in RNNs? You give input, but then computing all these H's, they are giving kind of contextual information to, so they are adding this contextual information to the initial embeddings that you had supplied. So whatever this final H of Tx was, that is carrying the whole information of this sentence. That is much more than just the summation of all the word embeddings. Okay. The animal didn't cross the street because it was too tired. The animal didn't cross the street because it was too tired. What is this figure capturing? If you talk about this it, who can this it refer to? What can this it refer to? The animal. One more thing, it can also refer to the street. You and me know that in this case it refers to the animal, but how will you make machine learn that? Because machine has got the same word embedding for it, so it does not really differentiate. Now in case of attentions, you can see, so these are attention weights, and the darker the line, more attention there. So if you see it, in this case it gives more attention to the animal rather than to the street or any other word. So attentions, they are really holy grail of deep learning these days. And what else? Maybe you can make a sentence in which you have two it, one refers to this and another one refers to the street, and even in that case it turns out that the system will be able to write it to right noun. Okay. I just wanted to show this figure, that's it, nothing else. What attention captures. Okay. All right, come next. So attention is parallelizable and solves bottleneck issues. Attention treats each word representation as a query to access and incorporate the information from a set of values. This is something we have already seen. So how does attention actually work? There is a query, so let us call this query. Where does this query lie? Who queries attention? So S1 you can call as a query, okay, because that person, so they are calling the one that this vector you want to attend to which one. So in this case, S is the vector right? So this is our query vector. You are querying each and every edge here, which one to focus on, okay? So there are three terminologies here: query, key and values, that we will subsequently come to. So we are gradually moving towards transformers now. Most likely next class I will introduce them. So we saw attention from decoder to encoder. Today we will think about attention within a single sentence. So we saw attention in a single sentence. Now let us talk about it. Number of unparallelizable operations does not increase with sequence length. So if you have something like this, this is my input sequence. How we were doing attention until now? So there is a encoder part, there is a decoder part, and you are querying from decoder part, okay? So we are going close to self attention now. What self attention says, why do you need these two counterparts? So why do you need something in the encoder, something in the decoder? Because that way you are able to do this only for maybe, let us say, translation problem, maybe for image captioning. But attention is a much more general technique. So this is your first layer. So think of this right now as an RNN, where H1s are these things, but I will quickly say they are not. So this is your input, one sentence, let us say. This is just one sentence, there is no decoder now. How can you take attention in this? Right. So this one, I always do this. Right. So this is your input, one sentence, let us say, okay. How can you compute attention for all of these guys? Because now you do not have a query from the decoder. So what you can do is, so you will compute an output here. So how many outputs still? Tx. Yes. Sub? वर्ड2x
नहीं वर्ड2x भी पहले जो सबसे पहली था जब आपने वर्ड2x
क्या था उस क्लास में?
सर उसके अंदर एक बार बोला था कि ना किसी ने तो बोला ना कि ना सबका एक दूसरे से डॉट प्रोडक्ट ले लेंगे वही तो करते हैं.
He is the dot product guy. हाँ.
दो वर्ड का डॉट प्रोडक्ट लेंगे उनका जो भी आंसर आएगा उससे उसकी सिमिलरिटीज पता चलेगी. ऐसे कुछ बात कर लेते हैं.
Okay. So see H1 what becomes query? Forget query, we will formalize this in the next class. Right now we are just trying to get the idea. So what do you do here? You want to compute this output. This whole thing, what is it? See, I want you to refer to this example that we were doing. The animal didn't cross the street because it was too tired, and the animal did not cross the street because it was too tired. So in right hand side you saw it, and then referring to everyone, and then there were attention scores given as the color of that edge. Okay. How do you compute such things? Because it is the same thing. So how do you compute these values for all of these now?
जैसे कि अपन ने उसमें किया था डिकोडर
So this is your H1. If I multiply, give me the math now. If I multiply H1, I hope I am doing it right. So if I multiply, see,
सर S1 की जगह H1 लगा दो
exactly, right. That is what we are saying now. H1 transpose H1, that will give you one number. What else? H1 transpose H2, that gives you another number, and so on. So basically H1 transpose HTX, and in our vectorized notation this whole thing was just, so let me just, this was H1 transpose H, where your H is H cross Tx. So this whole thing is going to give you a vector of size Tx. And what does this vector mean? How many of you are not following what we are doing in last 5-10 minutes? So bola karo na. See, earlier we had S. So you were taking dot product of this S with everyone in the encoder. What we are saying, there is no S now, okay, and we still want to be doing the same thing. So what we are saying, you are limiting attention mechanism to a kind of architecture where you have encoder and a decoder. There can be other problems where you don't have this architecture. So does it mean attention does not apply? It turns out it does. What you can do is, so we were multiplying with all H's anyway, this part you remember. So we had S transpose H. Instead of this S, just use this one vector. So this is my vector I am going to dot product all these other guys representations with. What will be the output of one vector here? So what will be the output of first computation? What will be the output of this computation? This one. 1 cross Tx. So 1 cross Tx, and why do you want it to be 1 cross Tx?
तो वो हर एक के साथ जो उसकी अटेंशन पता
आउटपुट जो जैसे डिकोडर वाले की बात करें तो हर वर्ड के लिए आउटपुट आएगा ना, तो 1 क्रॉस टीएक्स सबका अटेंशन स्कोर बताएगा कि मतलब एक पर्टिकुलर आउटपुट के लिए क्या अटेंशन स्कोर है, मतलब
Right.
क्या attention है,
Right, right.
1 क्रॉस टीएक्स शायद वो आएगा, और वो सबके लिए हुआ तो सबका आउटपुट है।
Exactly. So you will have 1 cross Tx here, okay, 1 cross Tx for this guy as well. So if you want to vectorize this whole output, how will it look like? Tx cross Tx?
सर बट वो भी तो था ना कि जैसे ट्रांसलेशन में बात कर रहे थे तो सेम वर्ड ही नहीं है,
Same?
मतलब लेंथ सेम ना हो, जैसे टीएक्स इनपुट था तो टीएक्स वर्ड ही आउटपुट में ऐसा
Right. हाँ.
तो उसमें टीएक्स तो टीएक्स कैसे बन सकता है, क्योंकि दोनों इनपुट इनपुट ही होता है।
See what we are, So I have not told you the name of this guy right now, what we are doing. This is called self-attention. So that earlier attention that we have done, that is called cross attention, because you are taking attention between something that you are calling as a input, something that you are calling as a output in your another language, in your target language. Okay. In this case, all we are asking this question is whether doing this makes sense. See, as of today, the deep learning is done. There is no way to theoretically prove whether this will work or not. So what is the way? You have this idea, code it, train it, and show that your system actually works. And this is true for every damn thing. So for every paper, every seminal paper that you see, there are thousands of other ideas that have not worked, but that one idea worked. Okay. Now, so this is going to give you 1 cross Tx. I still see some confused faces. This one? So are you okay if I say S transpose? So if you are okay with this, just replace that S with H, because there is no S right now. See, I have just written this encoder part. Decoder part I would have written here, but I am saying there is no decoder part. Then question is, can't I take attention now? The answer is, there is an idea and let us explore whether it works. And it turns out it works. Okay. So all these are exactly. So this is H1, H2, H3, H4 and so on. Okay. Now we are saying I have Tx, H vectors. How do I take attention? Because I don't have S now. So you don't have S. Somebody comes up and says, why don't you just take a dot product with H1 to see the output of this one? And now consider this was the animal and blah blah blah. Let's say somewhere here there was it. Now it makes sense for this guy to attend. So see, in the end deep learning is about learning representations. Okay. So right now you have these representations, these vectors here. The next layer will learn some other representations. So when you are trying to represent it, word embed, okay, let us put it this way. The word embeddings in some sense of it should be closer to the animal. So whatever the word embeddings of this, the animal, whatever, not word embeddings, whatever is the representation of the animal is, it should get a similar representation. Does this make sense? See, the animal didn't cross the street because it was too tired. Okay. Now T refers to the animal. So now you look at all the vectors that you are dealing with. Okay. Now, yes. I thought ki I'll do away, but so this is H cross Tx. Tx? H की dimensions, right? हाँ. Okay. So then the representation of it for this particular circumstance should be same as the animal. Now let's say for whatever reasons it in this sentence refers to the street. So in that case what should happen? The representation of it should change itself to the representations that is closer to the street, right? And this mechanism gives you that flexibility. Because right now if it pays attention more here, that means attention scores are higher for, so alpha 1 and alpha 2 is greater than any of these, probably significantly greater than any of this. But let's say if this it were supposed to represent or refer to the street, in that case what will happen? Alphas for the street will be higher compared to this one. So here you get something. What will be the exact output from here? Give me the, the dimensions of the output.
जिसका मतलब सर जिसका टेंशन सबसे ज्यादा होगा वो आउटपुट में आ जाएगा तो 1 क्रॉस 1 ही रहेगा लेकिन उसका H1 ही ऊपर आ जाएगा.
So what is the output that you want? Do everything same as we were doing before. So nothing has changed now. Encoder, decoder was there is no decoder now, and you are doing everything same. So this gives me a 1 cross Tx vector. Now do I stop there? This is what were we calling this? This was attention scores. So these are my attention scores. What do I do next? Softmax. Okay. So basically these are my attention scores, and then I take softmax. So softmax gives me, so basically this distribution, whom should I give how much weightage, okay, for just this one. Now what else? How do I compute this final output vector? Same old thing, alpha 1 times H1, alpha 2 times H2, and so on. So the final dimensions of this will be same as any other H. 1 cross? No. See, softmax you took. What are the dimensions of this softmax vector? 1 cross Tx. See, attention scores you have 1 cross Tx. You take softmax. So softmax does not change the size of the vector, that remains 1 cross Tx. Now this vector 1 cross Tx, so alpha 1 times H1, alpha 2 times H2, alpha 3 times, all the way until here. You multiply and then you sum. So what will be the resultant vector? Size same as H. So if all these guys they belong to R to the H, then this guy will also belong to RH, not R to the H, RH.
सर अपन समीशन करेंगे कुछ आउटपुट आएगा तो फिर अपन डिसाइड कैसे करेंगे कि किसका अटेंशन कितना ज्यादा है और आउटपुट डिफाइन करेंगे.
I don't get this.
सर जो अपन ने इनपुट दिया ये जो आउटपुट आएगा वो कोई भी H1, H2, H3 इनमें से किसी के बराबर नहीं एग्जैक्टली इक्वल नहीं होगा.
Yes.
तो सर अपन
Why do you want them to be exactly equal?
नहीं मैं चाहता हूं पर
Okay.
आपको पता कैसे लगेगा कि सबसे अपन फिर जो ये क्या कहते हैं अटेंशन असाइन कर रहे हैं हर एक चीज को वो कैसे असाइन करें अल्फा से.
Can we take this offline? I don't understand this again. So
सर एच का डायमेंशन क्या लेते हैं? 100 क्रॉस 1 क्या है?
H is 100 cross 1 usually in art. So H is that same guy which was 100 cross 1. Now you have actually input. So H is that hidden layer thing 100 cross 1. But still when you begin with, so you will feed the as the word embeddings, which was 300 cross 1, which was 300 cross 1, animal, which was 300 cross 1, and you subsequently, so see, this is same as RNN that we had written. From here you get an input that is 300 cross 1, you process it to make it 100 cross 1. So what is passed as 300 cross 1 is the word embedding, but we know there are so many shortcomings with word embeddings, so you need to keep on you need to keep on changing the representations, you keep on refining them.
सर एक्चुअली ये पूछ रहे हैं कि इन सब का अगर हमने सम करा
Hmm.
फिर हमें उस सम से ये कैसे पता चलेगा कि हर एक उस अटेंशन को कितना वेटेज मिल रहा है?
But in principle, why do you need that?
आपने बोला ना सर सम करना है,
Yes.
तो फिर पता कैसे चलेगा किस अटेंशन को कितना वेटेज मिला है सम से?
And why is that a problem?
आउटपुट कैसे डिसाइड करेंगे कि क्या आएगा?
Which output are you talking about?
सर इससे भी तो कुछ आउटपुट निकलेगा ये जो आपने ऊपर वाली लेयर बनाई है,
Right,
इससे कुछ आउटपुट आप ले रहे हैं,
right.
तो सर इसके अंदर आउटपुट अपन कैसे डिसाइड करेंगे?
Right now, I am not talking about that. I am just talking about self-attention. So, this you won't need alone. This will be coupled with a lot of other things too. Right now, we are just learning representations, and right now we are just learning what is self-attention. That's it. What will you do with what vectors you have? So, what you can do again is, this was your first self-layer attention. You can have another one. Compute self-attention in the same manner, compute that same vector of 100 cross 1 again. Okay? That, so those who have invented all these things, they believed this will improve the representations, and then it turns out it does. Okay? Okay, done for today.
इससे सेकंड में हम अटेंशन जो हमने लिया है तो तारीख का उसका फिर से हम ले रहे हैं,
क्या चीज?
मतलब हमने फर्स्ट
Class is over. Those who want to leave can leave. हाँ.